Hey guys, this will be the last set of notes that I need you to watch prior to coming to class on Thursday. It'll be volumes by known cross sections. So we did the discs, the washers. I introduced you to the shells. Shells will not be tested on my test or on the AP test, but it's good to have a little bit of knowledge about them. I will put visuals in for discs, washers, shells in a folder in Schoology that just says visuals or animations. I'm going to show you the known cross-section one that I showed you last year again, just to revisit what happens with the known cross sections. So remember what I told you to think about last year? We have this function or two functions intersecting. This red axis right here is the x, the green is the y. And then we're building up off of it. This is actually called the z-axis right here in blue. You don't really need to know that, but you need to picture like laying your function or your shaded region on the ground. I used to tell you to think about it like a bread pan. And you're going to bake up off of it in different shapes. And that's why they call it known cross sections. So if I choose the square, what'll happen is, sorry, I'm getting the spinning wheel here. Hopefully what'll happen is a square will pop up as if, I'm going to give it a little bit longer here and then I might try, let me try it again. There. So we're building up off of it with squares. So you'll see as I run this along, it's making a solid, right? And you can see it making that solid. And I can move this and I can make this what I called last year a bread loaf pan. And everybody, when I slice it, if you picture me slicing off little pieces right here, you're getting an infinitesimally thin wheat thin, right? Now, to find the volume of this, right, everybody's slice is just basically a rectangular solid. And we would do base times height. For a square, it would just be side times side. And then its depth is the dx. So it's still length times width times height. It's just for the square cross sections, it's side times side. And a side is the top function minus the bottom function. Look at the cursor. The top function minus the bottom function would give you a side length. All the sides on the square are the same. So if you did side times side, you get the area of the face. Its depth is the dx. So then let's try semicircles just so you can see it. So we build up off of the loaf with the semicircular shape. So if I were to slide this sucker, if it'll let me here, let's slide it along. Come on. There we go. You can see it making this dome. Now this time when I cut it and I give you a piece of this bread, you get like a semicircular piece, kind of like French bread. And the area of the face is half the area of a circle. So we're going to talk about it. Its depth is still dx. You always do area of a face times the depth. And then the integration will add it all up from left x to right x, or the intersection of the two functions. So let's go take some notes just to bring it back. And again, we did it last year. We're just going to spend an extra day, I think, because like I said, we didn't review this last year for the AP test. So I gotta move over to my smartboard. So when we're finding the volume whose base is bounded by, and there'll be a region, and that region will be given as, like, say, y equals the square root of x and x equals 1 or something. So we graph that region and we shade it, and we have cross sections that are going to be a certain shape. Depends on when you cut the loaf, right? And they're always taken perpendicular, and it'll say which axis to. So it'll say either to the x-axis or the y-axis. Well, to get the volume of any solid, you need the area of the face, and we call that A of x. That's the area of a face. Now again, if you were to think of just a box from elementary school, the area of the face is a length times width, and then its depth, right, is the height. So it is area of a face times the height. Same with, like, the volume of a cylinder. It is the area of a face. In this case, the face is the circle, right? If you were to slice it like this, times the height. So even your geometric formulas sort of have that same area of a face. The height for us is dx or dy. Again, if you're going perpendicular to the x-axis, the dx. If you're going perpendicular to the y-axis, the dy. We add them all up from A to B. This is the volume of one slice. This is the area of the face of the slice. Let's go take a look. Shapes determine the area. So almost always there are shapes. Sometimes they'll just give you a formula and they'll say the area of the face is sine squared. Well, then you just, sorry, not sine squared dx, sine squared x. Well, then you would just say, well, here's the area of the face. Area is 2 dimensions. Here's the 3rd dimension. So that's best case scenario where they just tell you this is the a of x. But remember for the square, and the sides are the same. So the area of a face is just side squared. For an isosceles right triangle, it's half of a square. So we just do half of a side squared for the area of a face. Now, for the semicircle, we would do 1/2 of pi times the radius squared. And we'll talk about that on the next page. For the equilateral triangle, all right, so let's mark that equilateral triangle. That one sometimes people have a hard time remembering, so we will, maybe I'll derive that one for you. Let's call this a side and a side and a side. And for the equilateral triangle, let's drop this down. It makes a short side that's a half, right? These are equal. In an equilateral triangle, when you pop it down, the long side still is always the short side, √3. So this would be √3 over 2 times the short side. Because remember, that's your 30, 60, 90 relationships. That is all about, I'm going to take my mask off, all about that short side. And the hypotenuse is twice the short side. Again, if you're like, I didn't remember that. Well, that's because it's been a while since you had geometry. But the hypotenuse is twice the short side. And the long side is the short side times the square root of 3. Now to get the area of a triangle, we do 1/2 of its base times its height. So we would do 1/2 of its base, which is s, times its height, which is the √3 over 2s. So we get √3 over 4 times a side squared. And we'll talk about this guy on the next page. We'll sort of derive that. This says AP alert. Be careful if you're given a function for a of x. I think that might be awful. That happens sometimes, like I said up there with the sine squared. That's happened on the AP test before, where they'll say the area of a face is natural log of x times, I don't know, 3x or something. And kids are like, well, I didn't know what shape that was. Well, that's the area of the face. This is already like the length times the width, or the 1/2 pi r squared. It might just be some funky shape, and we're doing the volume of maybe a lake. Boy, that's a pretty lake, right? But you still do the area of a face times the depth. And so that would just be integrating this dx to get my volume by cross sections. So I'm not going to do this one today. I feel like the notes have been kind of long. So suppose we had these two functions, f of x and g of x, right? And they crossed like this, and so my shaded region is the area bound by both of them. So when I go to my shaded region, I'm going to go grab a highlighter here, guys, and we'll shade it in. We did this last year, and we did actually these exact same notes, but, and again, you can always, maybe what I'll do for those of you who this isn't coming back with just these recap notes is maybe I'll post last year's Chapter 7 videos, so if you need more, where we actually went through it really slow. I just don't think most of you are going to need that. So what I have there is the bottom of my bread loaf pan, basically, is what I said last year. And you have to picture laying that flat, like on your desk. And you're going to build up off of it so that when you slice it perpendicular, let's say to the x-axis, you do a vertical slice through it, you will have a square piece. Now that's not the best drawing because I'm trying to picture it popping out of the paper, but regardless, if it's squares, it's going to look like that with the sides the same. So the area of a face would be side times side. Now look, the side length of the side is just f of x minus g of x, top minus bottom. So for all of these that I do, our side length that we use in our formula is just going to be top function minus bottom function. If I do top function minus bottom function, I will get the length of this side, right? Because it's y equals f of x, y equals g of x. The change in the y values is the side of the square. Well, how do I get the area of a square? Because remember, we integrate the area of the face, right? And then we give it its depth. So if it just says that the cross sections are squares, that's the easiest because we just do side squared. And the side's a function of x if you want to put it like that. What I mean is, had this been maybe an upside down parabola, negative x squared plus 4, and maybe this was one that opens up, x squared, I don't know, minus 1, right? To get the side length, I'd subtract those, and it would be a function of x. All right, so I'm not sure why I have such a thick marker here. Let's tone her down a little bit. And then this gives you its depth. So 3 dimensions, 1, 2, 3 for volume. And we'd integrate from intersection. And again, if you're doing that without a calculator, you would set f of x equal to g of x, and it will factor. If you have a calculator, just use calc intersect on your calculator. So for squares, it's just a side squared. All right, so let's go to the next one. For the isosceles, there's 2 different ones, and it depends on whether the leg is across the base or whether the hypotenuse is across. My marker's being really weird. I'm kind of digging this green though, but I'm going to go grab a highlighter right now. All right, I'm just using all kinds of colors. So go shade this in. Let me go to a thicker. All right, there we go, sorry. So I will go shade this guy in. And again, this is the base of the solid. And we're going to be building up off of it with different geometric faces. In this one right here, we're going to do isosceles right triangles with a leg across the base. So remember, for isosceles, the 2 legs are equal. So it'll look like these things basically popping out. But remember, this is a side length, top minus bottom, and so is this. And for the area of a triangle, we do 1/2 of the base times the height. So it's really just half of a square that you're eating. You're eating like a Triscuit's triangular, or like a Dorito, right? And then, so there's 2 dimensions are still side by side. That's the area of the face. Take half of it because it's half of a square, and then give it its depth, integrate from A to B. And again, the side is just top minus bottom, or f of x minus g of x, and that will hold through all of these. So what if the hypotenuse is across the base, right? Then what we have over here is the hypotenuse is across the base, and we've got the sides kind of coming like this. So when the hypotenuse is across the base, we actually end up with a 1/4, and I could derive it for you, but I did that last year. If you want to think of it as this is half the square, but when the hypotenuse, sorry, this is looking really bad. When it's like this, and the hypotenuse is over here, it's 1/4 the square. And you can do a geometric proof of this, but I would just memorize that when the leg's across the base, half. When the hypotenuse is across the base, 1/4. Now for the semicircle, let's drop this down. Then we're popping this up here. The diameter of the semicircle is now what we'd call S, top minus bottom. Remember, the area of a circle is pi are squared, but we're having semicircles. And furthermore, our radius is 1/2 of a side that we need to square. So that when we clean this guy up, we have 1/2 from the semicircle, and then we end up with 1/4 from squaring that. So we end up with 1/8 and the pi and the s squared. So last year I had you memorize that there was a pi/8 multiplier out front for semicircles. So again, squares, s times s. Leg across the base, isosceles triangle, 1/2 of a square. Hypotenuse across the base, 1/4. Semicircles, pi/8. And do I have another one? Equilateral triangles, I showed you on the other one. That's when all of these are the same. This one rarely gets asked on the AP exam, but it's √3/4 and then a side squared. You'll notice they all have that s squared in them. It's just whether it's squares, just s squared. Isosceles triangles, either 1/2 or 1/4. Semicircles, pi/8 multiplier, and the equilateral triangles has a √3/4. Some kids think it's √4/3, and I'll be like, well, then it'd be called 2/3. So if you're debating between the two, this is the one that's least likely to be asked on the AP exam. I've seen it, but I have to go back really far. But I'm going to add another one to this because sometimes, albeit rarely, but again, I like to have you over-prepared versus under-prepared, they'll have you build up off of the base so that your cross sections are rectangles, like club crackers or graham crackers. And let's say if they do that, they have to give you a relationship. So again, this is still S, or the side. We still do top minus bottom. But what they'll say is whose height is maybe triple the base, or whose height is 1/2 the base. So it'll give you something like that. So here's your graham cracker, and again, it's popping up off the base like I showed you on that animation. It's really hard to draw two-dimensionally. Actually, it would be better if I sort of skewed it. Let me try doing that like this. So these are popping up off of it, but you still need to do the area of a face. Now, if it said it was 3 times as high, right, whose height is 3 times the base, then your 2 dimensions, the area of that face is base times height, which is triple the base. Its depth right here, it's like little depth, is the dx, and we add it all up from intersection to intersection. Wow, that is pretty cool, right? All right, so let me go see if I have a sample. I might not. I might have to actually. That one I did in the notes already. Yeah, so here's actually some better visuals. So we'll talk about those in just a second. I want to revisit the area of a region bound by 2 curves. So remember, when you're doing the area of a region bound by 2 curves, again, we're not building up off of it. We're not doing volume anymore. I just want to know what is the area. That's the easiest. The volume's a little harder. But if I wanted to know what's the area of this, remember, it's all about, one of the biggest things with calculus is that we can add up an infinite amount of rectangles as we go from left to right. They have a height of the top function minus the bottom function. So if this was f of x and this was g of x, now again, if it's butting up against the x-axis, then the bottom function is 0. So if this was the square root of x, and I was finding the area of this, right, I'd integrate, let's say, from 0 to 9, right? From 0 to 9, top function minus bottom function dx. It's just f of x dx. What that does is the f of x, right, is the height of the rectangle. The dx is the depth. And if I added up an infinite number of these rectangles from left to right, making their dx approach 0, right? So their depth approach 0, I will get the exact area under the curve. Now, when one of the functions isn't the x-axis, we'll still do, well, what is the height of the rectangle? And we say we do top function minus bottom function, right? That's the height of the rectangle. Its base is a little change, or a little dx on the x-axis, a differential. The difference between delta x and dx is this is infinitesimally small, this is any change in x, but they're both changes in x. You might say, well, that's not very small. Well, that's because I didn't draw it. I mean, I'd have to go get the thinnest tipped pen ever. All right, and we integrate from intersection to intersection, from A to B. Again, without a calculator, we find those by setting f of x equal to g of x. Things will factor. You'll get one side equal to 0. With a calculator, we use calc intercept. And you're going to be practicing that both in Delta Math and on a worksheet. So last step, find the area of the region bound by e to the 3x, the x-axis, the y-axis, and the line x equals 3. Well, what does e to the 3x look like? Well, first of all, it's an exponential function. E is like 2.7-ish, right? So I'm going to write the about 2.7-ish to the 3x. So when x is 0, it would be up at e, so this would be like 0e, and then it's going to grow exponentially. As x goes negative, it's going to be 1 over. So it's an exponential growth curve with a base of e, and it's being really stretched out, as you learned in pre-calculus, because of that 3. Well, we need to find the area bound by, back to a different color, the x-axis, the y-axis, and the vertical line x equals 3. So let's go shade that in. We want the area of this green stuff. We're not revolving it. We're not building up on it and having a volume by cross section. I just want to know the area of the green stuff. So basically what I'll do is simply integrate from x to x. The height of the rectangle, top minus bottom, is e to the 3x minus 0 for this one, because this is, see, it's just the height of the function. Its depth is dx, and that's it. Okay, we'd be adding up a bunch of rectangles whose heights are e to the 3x and whose depths are dx. So let's integrate that. Be careful, this is u sub. U would equal 3x. Now, if you want to change limits, which I like to do, I'll go from 0 to 9 and I'll never look back. Du is equal to 3 dx, but I just want dx, so I do 1/3 of my du equals dx. So let's set this up. We now have e to the u for this guy. This guy is 1/3 du, fraction correction out front. And now our u limits are 0 to 9, and now we need never not go back to x. The antiderivative of e to the u is e to the u. That'd be e to the 9th minus e to the 1st. And then remember, I had the 1/3 correction in front of it, so 1/3, and don't forget to parenthesize. If you math 9'd this on your calculator, you will get the decimal version of this exact answer. All right, so that's the last one on cross sections, volume by cross sections, and just area between two curves. Next up is going to be on Thursday, practice on a worksheet, primarily with discs and washers, and then we'll do some Delta Math on Friday. All right, so have a good one.